We announced we have one more talk in this session. The one scheduled usually to 5 p.m. is holding people now by Dario Billy. So he's from ESA. And he will talk about 3D reconstruction of underwater shipwrecks, 3D Gaussian Splatting, structure for motion on the Melania shipwreck.
Thank you for your introduction. And good morning everyone. Today I will present this work that regards the 3D reconstruction of underwater shipwrecks within the aquatic methodology that integrates the structure for motion pipeline within the Gaussian Splatting for, in this case, an existing data set, the Shipwreck. As I said just now, the objective is to integrate this traditional structure for motion photogrammetric methods that is focused more in metric accuracy with the Gaussian Splatting techniques that is focused on realistic real-time rendering. In this case of unexisting old dataset. The method uses a shared set of camera alignment parameters for both the pipelines. This study is the Melania shipwreck located on the Vada coast in Livorno, Italy, and the survey was conducted in the past by Soviet team. As the dataset provided by Soviet was captured using GoPro cameras, optical divers, and several underwater video sequences were recorded in order to extract high-resolution frames. Also, a color correction was performed by the use of photo-realism, adjusting white balance adjustment, and all the RGB channel integration. Here we have the overview of the proposed methodology, and as you can see, we have in different color the pipeline and the standard structure for motion pipeline over there, and here the methodology based on the use of Gaussian Splatting techniques. With the common, both the pipelines have started from a shared sparse point cloud generated, as I said before, from the main alignment. In this case, typically this is done with the use of colmap, as we know, but we had many issues and problems where colmap used to fail to properly align the image. That's why we decided to adopt a solution with structure for motion proprietary software, in this case a software shape. I don't start anymore with this process because all we know how we generate the model after the sparse point cloud, and when we capture it with the triangulation and mesh generation. So just to show how it concludes this part of the pipeline. While for the other pipeline, I want to spend more words. As you can see, we start always from the generation and the camera internet external parameters and the sparse point cloud. That inside, thanks to a script, inside the readable structure folders can be read by 3GS pipeline. The initialization, so we will just explain some steps, basic steps, to explain better how it works. There is an initialization where the points are converted in 3D Gaussians, starting as spheres, that contains not only the X, Y, Z position and the RGB, but also other information. For example, sigma that indicates the matrix of covariance, that is an isotropic covariance, or sigma in fraction of alpha that contains the range of transparency between 0 to 1 range, or for example also the spherical harmonics. In the second step, there is the projection and the rasterization of these first attempts Gaussians in 2D Gaussians, parallel to each frame image, creating the first rendered image. In the first step, there is a comparison between these resultant images with the original ground truth image. That thanks to this, there is the computing of loss function to adjust the Gaussian values in the second, third, and fourth iterations, and many others as we want to set it. The fourth of the steps is an adaptive density control, that is an automated densification for more precise details, for example, or the pruning of 3D Gaussians that are, for example, too transparent and not useful. These 4 steps basically are all linked by iteration process, and until the loss function, until the rasterized image are really close to the original image. To note is that the 3DGS in this case was run again on the prompt. We used all default settings except for the image resolution that was reduced to 1/8 due to a large amount of image and size of the dataset. The automatic pruning of the superfluous Gaussians during the iteration sometimes can be often insufficient. So we also try to propose to go inside a Supersplat, that is an open source platform that was used in this case to inspect and selectively edit the splats directly within the interactive environment. In this case, I want just to show visual results that you can see in the first to your left column. We have the model, the 3D model with the use of raw images. Here we have the central column with the integrated image, but inside the instruction for motion with the software. And here we have the 3D Gaussian splatting with still the color calibrated images. The same one, of course, as I said since the beginning. Just here we have another detail of the racks, and as you can see, there is a kind of good saturation and chromatic variety. So the 3DGS model produces kind of more vibrant and perceptively engaging imagery, particularly in areas that are kind of most affected by the depth-induced light inclination. Also, we introduced the rendering metrics for this pipeline. Yeah, thank you. And we decided to compare it with metric quality threshold in this table that are indicated and estimated using a reference, some others, plugins and implementation of the Gaussian splatting that still aren't available with the code and others. Experimentation of water splatting and sea splats. In terms of time processing, as you know, the image alignment is, as you can see even here, the most time-consuming step. While for the generation of the solid and texture model, takes twice long compared to the creation of the synthetic model of the Gaussian splatting. In conclusion, the advantages of this methodology is to generate 2 models that can be, in this case, complementary models. In terms of the first one for suitable for metric and scientific studies related to archaeological purposes, for example, while for the real-time rendering model, an improvement of color rendering with the reds and warm tones, for example, that can help to more easily detect and identify specific kind of flora or fauna settling in the wreck. As to the words, this is the last slide. We want also even to include the generation mesh model from Gaussian splatting that here in this example we already tested in our research on this retrospective dataset that was regarding the transparent surfaces from native code with the implementation of sugar or to the Gaussian splatting to also do all the metric accuracy analysis, etc. Also a greater replacement of free software and the extension of these pipelines to more complex and dynamic scenarios, also more controlled by us. Thank you for your attention. Here we have just some reference. Yes.
for instance, if it's possible to see some sediments or something like that.
Sorry, the last words I didn't.
If you can identify some sediments or whatever, usually the low alpha transparency values on the photo.
Yeah, still is in working in progress also these features that you just said, and we want also to experimentally, if it is possible, to also detect these particular phenomena. But we are exactly in the beginning of this workflow. In fact, we want also to have metric accuracy, etc., generating also the mesh, and not only by the point clouds, the past point clouds of the Gaussian Splatting, as we know by other contribution can be exported, but still we are in ongoing works about this.
If you export the point cloud from the Gaussian, 3D Gaussian Splatting, it might be a good idea to reconstruct surface. There's 3D Gaussian Splatting, for instance, which is much more appropriate.
Yes, as you saw here from the results of the battle investment plot.
Thank you.
Okay. Seems we are kind of separated.
Sorry.
Thank you again.